you could share your screen.
Hello, sir.
Hi.
Hello, sir. Hi. Am I audible?
Yeah, we can hear you. Can you share your screen? And
Yes, sure, sir. Sure.
yes, okay. And thanks, and Pawan, thank you very much for your talk as well. I should have said that. Yeah. Yeah.
Thank you.
We can't see your screen. We're about to see your screen. That's great. Yeah, and if you can go to full if you go to full screen and then start. I can hear you. I'll just confirm I can hear you though. So but please start.
Is it okay?
Yeah, it's great. It's perfect. Please start.
So first of all, good evening. Good evening, all of you. Myself, MD Mouzakkir Hossain from Harbin Institute of Technology, China. The title of my talk is Instability Mechanisms of Shear Layered Fluid Below a Floating Elastic Plate. So, one second. Okay. So basically the idea is to use the instability control strategy by placing a floating flexible plate or membrane at the top surface, which is a control technique to stabilize the most unstable surface wave mode or unstable modes. The idea is to study the flow dynamics of shear waves in both cases, like viscous and inviscid cases, which can be used in examining the flow behavior or instability dynamics below floating elastic plate. Also to understand the instability mechanisms of both shear layered viscous and inviscid fluids in the presence of floating elastic plate using the energy budget analysis. So basically this work is not basically totally fully on the water wave problems. This is basically the application is basically the coating of elastic surfaces or collapsial tubes. Or basically, and best what example I can give you that if you someone create that efficient or most accurate that coating at the elastic surfaces, so one can use this model. Or also it is used in the microfluidic devices or cardiovascular and lung flow in the biomedical industries. But in a large scales, the floating elastic plate this idea can be used. This because this idea one can understand the mechanism is the hydraulic instability mechanism of floating elastic plate, which can serve as a practical model for frozen ice or very large structure on the ice, on the sea. So first I'm going to the sketch of the model and then basic assumption for its mathematical modeling, then formulation of the problem, method of solution, results, and then references. So this is the shear layered fluid model. This is in the Cartesian coordinate system. This fluid is flowing. This fluid is not flowing due to the gravity. It's flowing due to the air shear, which is surrounding, that means the surrounding air. At the free surface, we have considered the floating elastic plate, and eta, the z equal to eta xt is the thickness of the fluid flow, and h, this is the mean film thickness, and g is the gravity which acts downwards. So this assumption is incompressible and shear layered fluid down a slippery substrate at the bottom, and a floating elastic flow thin ice sheet at the free surface, and the bottom wall is basically we have considered the slippery, which may be either it's maybe porous type or like a cracks or simple cracks, which is that range of this parameter of the wall slip is basically from 0 to 0.3 in this work. So idea is to, what is the target? Target is to stability instability mechanism of the fluid flow, the effect of floating elastic plate, characteristics parameter like the structural rigidity alpha and the uniform thickness gamma on the fluid flow below the floating flexible plate, and the effect of slip parameter on the plate covered surface. Okay. So these are the governing equations. This 1, 2, 3 is the equations of motion for the fluid flow. And since this is an open type flow, this is not a channel flow, so this is open type flow. So there will be obviously that free surface boundary conditions, like 4 is the kinematic boundary condition and 5, 6 are the dynamic boundary condition. U and W, we have considered here that flow velocity along the x direction and the z direction, that is the vertical directions, and rho is the density of the fluid, and mu is the viscosity of the fluid. Here in equation 6, you can see capital EI is there. This is the structural rigidity of the plate, and capital N is the compressive force acting on the plate, and MP is the uniform thickness of the plate. And since we have considered the bottom is slippery, so that's why equation 7, you can see U equal to kappa uz and W equal to 0. Here kappa is the slip length. So this is a non-dimensional form. So basically we have reduced these governing equations to the non-dimensional form to reduce the complexity of the nonlinear differential equation. And by doing this non-dimensional, we can get the flow parameters by which it will be easy to characterize the fluid flow, that means instability of the fluid flow. So this is the non-dimensional form, equation 8 to 14. And capital R is the Reynolds number, and tau is the non-dimensional form of the external shear, and alpha, beta, and gamma are the non-dimensional form of the structural rigidity, compressive force, and the uniform thickness respectively. Okay, this is the so basically in linear instability analysis, what we do, we are perturbing the laminar flow. Basically, we are perturbing the laminar flow or steady flow. So first we have to we have to derive the base flow solution, which is given in equation 15. This is a linear base flow profile. UBZ equal to tau z plus delta. And since we are perturbing the base flow, so we are taking the linear perturbation of the base state, which is given in equation 16, where UV and PB are the base state, and this tilt symbols below this WP and eta are the perturb state or perturb flow variables, which are very small. Since we are dealing with the linear perturbations or linear stability analysis, so we are considered up to that linear perturbations. Now substituting this equation 16 into the non-dimensional form, equation 8 to 14, we'll get the linear perturbation equation 17 to 23. Now we are using this normal mode form. We know that the flow there is the perturb flow variables has a relation with the stream function that U tilde equal to del psi by del z and W tilde equal to minus del psi by del x, where psi is the stream function, and that the zeta is the free surface deformation amplitude, which is given in 626, and 27, 28 are the relations of the stream function amplitude with the perturb flow variables. So from here we can get here k is the basically k is the wave number. Sorry, where k is the wave number. This is a real number because we are see this is the two-dimensional flow. So basically here k is the wave number in the flow direction, and c is the complex wave speed, and k omega I equal to kc is the growth rate of the perturbations. So if omega I less than 0, that means the disturbance is, if less than 0, that this disturbance with respect to time is decaying exponentially. That means the flow will be linearly stable. And if it increases like exponentially, that means it will be unstable. And if it is 0, then the fluid will be neutrally stable or marginally stable. That means it's neither stable or unstable. So after substituting this normal mode from 24 to 28 into this linear perturbation equation 17 to 23, we'll get these ordinary differential equations 29 to 33, which is basically called the Sommerfeld equations, or we can say the Sommerfeld eigenvalue problem. This equation for viscous fluid, because you can see the RE is there, so RE is basically finite here. So these are differential equations of the perturbation of the stream function amplitude and the surface deformation amplitude. Now for here also we have started that for inviscid case, here Reynolds number is tends to infinite. That means the viscosity is very low. That negligible viscosity. That means this equation basically, which is given in 34 to 37. This is the second order differential equations with the boundary conditions. Now to handle these problems or to solve this differential equation for both cases, like viscous case and inviscid case, there are two techniques like numerical and analytical techniques. For analytical techniques, one can use the long wave expansion method, and for numerical technique, one can use the Chebyshev spectral collocation method. But in this work, basically, we have used that Chebyshev collocation method. Basically, what we have to do is that we have to approximate the amplitude function, the stream function amplitude phi of the influenceable disturbance by the truncated series, which is given in 38. Then after substituting this 38 into this Sommerfeld equation for both cases, and that means that viscous and inviscid cases, we'll find this eigenvalue problem which is given in 38, where capital AX equal to CBX. Basically, C is the generalized eigenvalue of the generalized matrix A and B, and capital X is the generalized eigenvector corresponding to the eigenvalue C. So if one can find this eigenvalue C and the corresponding eigenvector, so one can find easily the growth rate of the linear disturbance, and from this eigenvector one can also derive that different energy components of the fluid flow. Okay. So these are the like eigenvalue spectrum plot for both cases, like viscous case, that figure A is for the viscous fluid and figure B for inviscid fluid. So for figure B, you can see that for free surface flow, the square shaped the eigenvalues are that is greater than 0 for free surface flow. But if you consider the floating ice covered surface or floating elastic plate at the top surface, that you can see that growth rate CI decreases. And also, not only that, on the phase speed also decreases, the CR. So for floating ice covered, for floating elastic plate covered surface, we can see that the surface wave is basically damped, and and its corresponding growth rate decreases. And for inviscid flow, you can see the growth rate is so high as compared to the inviscid fluid, viscous fluid. And for that case also, that floating elastic plate has a damping effect on the surface wave instability. So here basically we have validated the previous results of Smith et al. In 1982 for both you can see that for solid black lines and the dotted lines are for the corresponding results, and the blue dotted lines are for floating ice covered surface growth rate, that you can see the maximum growth rate decreases for the floating elastic plate covered surface. And also another thing noticeable here, that for shear layered fluid, you can't see any instability in the long wave zone. Always the instability will occur for the finite wave number zone and for high Reynolds number also. So this is the marginal curve, marginal stability curve here. In figure A, we have plotted the marginal stability curve. So each line basically draws that omega equal to 0. So inside the region, basically this is an unstable zone, and outside the region is the stable zone. And also here you can see that in the long wave zone there is no instability. So that means for shear layered fluid below a floating elastic plate, the instability only occurs in the finite wave number zone. And if we increase the rigidity of the plate from alpha 0.1 to 0.5, the instability is decaying and makes the flow more stable. And in figure B and C, we have plotted the corresponding growth rate results. Like we have chosen the Reynolds number from the unstable part of the figure A, and we have plotted the corresponding growth rate result, and we have shown that how this rigidity of the floating elastic plate decreases the maximum growth rate of the surface mode. And this is the comparison results between the viscous fluid and inviscid fluid for different uniform thickness of the floating elastic plate. So in figure A, we have plotted the inviscid fluid growth rate and viscous fluid. So you can see that viscosity has the damping effect. So always the viscosity, so inviscid flow has the advantage, and it is very difficult to control the inviscid fluid like surface wave instability. But for viscous fluid, the growth rate is very low as compared to the inviscid fluid. And the uniform thickness of the floating flexible plate decreases the maximum growth rate and makes the inviscid fluid stable, and for viscous fluid also it makes stable. And in figure B, we have plotted for different external shear force. So if we increase the external shear force or air shear from 0.1 to 1.5, so in both cases that we can see the instability of the surface wave instability increases as followed by the increasing the maximum growth rate of the surface wave. So also we have done that energy by analysis. So from since, as I told you, from Chebyshev collocation method, one can find that corresponding eigenvector, that means eigenfunction. So from eigenfunction, I can derive this all the energy components, which is mainly responsible for the instability that creates due to the air shear. So this which is given in 41. So each energy energy components is given in the integral form. So from this integration, we can solve this each and eigenfunction. So each components of the in this energy components is given in the eigenfunction form, where this like kin, T, par, dis, and is. These all terms are the energy components which is responsible either from Reynolds energy, like from hydrostatic energy like viscosity, and the other flow parameters. So, and we have plotted all the energy components with respect to Reynolds number and the wave numbers to check that in which part, in which either long wave zone or finite wave number zone, which is mainly dominate the surface wave energy. So these are some results for different energy components as a function of Reynolds number for different structural rigidity alpha. And we can see that in figure A, that like if we increase the structural rigidity alpha from 0.1 to 0.5, the Reynolds stress energy decreases in the finite Reynolds number zone. That means from high Reynolds number zone, and basically it's okay. Basically, it's actually it creates the damping effect to the surface of instability. And similarly, we have plotted in figure B, C, and D, like hydrostatics. That hydrostatic energy, like this is the basically dissipation to the viscosity, and this is the for external shear energy, which basically is the damping, which is damped by the structural rigidity of the plate. So these are the findings. The short wave instability is dominant for viscous fluid, but in case of inviscid flow, the instability is dominant in long wave region. The floating elastic plate is, or we can say that the thin ice sheet that reduces the wave energy due to the shear layer fluid. The stronger imposed shear has the potential to destabilize the fluid flow, and also the slippery surface has a dual impact, like stabilize, destabilize on the shear layer fluid. So these are the some references. Yeah, thank you for your attention.
Thank you very much. So there's plenty of time for questions. Does anyone have a question?
Yeah, Mohammed, could you please go to slide 6, the plate equation you have mentioned?
Okay. Yes.
Yeah, okay. So equation 13, it's not thin plate equation. It means this 1 plus eta x whole square to the power 3 by 2. This is for capillary gravity wave we generally consider. Beta is for capillary gravity wave. But alpha
Yes,
del to del x square means it is reasonable, or have you find it somewhere?
yes. Basically, this structural
Sorry.
rigidity applications like for microfluidics. So this is very not like a thin ice sheet, like just like a water. It's like a synthetic ice. So that elasticity, the rigidity of this ice sheet is basically the called that alpha, the rigidity.
Yeah, that's okay. But
What is
this
the
1 plus eta x square whole to the power 3 by 2, that
Yes.
term I am confused.
that's to do with the nonlinear bending though, isn't it? But what is that what's the second derivative, that alpha term? What's that from? That's another.
That is
This one.
compressive force beta.
Yeah. That's for beta. Yes.
And that notation there, where you've written the partial derivative xx squared, what does that mean?
That is like a double partial derivative with respect to x. This is like a different, it's like we have
I
used
wouldn't
like,
use that notation. I'd either have the square, or I'd just have the xx, because it makes me think it's the double derivative squared. So it's the fourth derivative. Okay, yeah, a bit confusing. I don't recommend that notation.
Yes,
So
okay.
did you how long have you been working on this problem? Because it's with these all Sommerfeld equations. Did you work in India on that problem?
Yes, sir, India, sir. This was also work problem in India. Normally I did.
And who were you working under in India?
For India, sir, Dr. Hare Krishna Behra.
Yeah. Okay, yeah, that makes sense. Yeah, I recognize this sort of all Sommerfeld stuff from him. Yeah.
Yes, sir. And
Very
basically, this
interesting.
basic idea I got from your work, sir. Whatever you
Yeah.
did in fluxual waves, from there I
Yeah.
got that.
No, it's very interesting. It's well, I'm not an expert on this problem because there's a nonlinearity, and then you linearize it and get this kind of strange equation that governs the growth. But is there any other questions? It's great that you were able to give your talk, that's for sure. So I think so some